You know, sometimes the biggest breakthroughs in science don't come from some brilliant master plan. Nope, they come from a complete and total accident. Today, we're going to unpack the story of an experiment where a clumsy lab mistake ended up proving a revolutionary idea that completely rewrote our understanding of reality itself.
So let's just start with the central question here, a real mind-bender that physicists were wrestling with back in the early 1920s. Is it possible for something we think of as a tiny, solid particle, an electron, to actually act like a wave? Spreading out, creating interference patterns. It sounds impossible, right? And it flew in the face of literally everything we thought we knew about the universe.
To really get why this was so radical, we need to take a quick step back and look at the world through the eyes of classical physics. It was a neat and tidy universe, It had clear, predictable rules for how everything worked.
Okay, so on the left, you've got that classical view. Think of giants like Maxwell. In this world, everything is simple. Matter is made of distinct little particles, like tiny billiard balls, and light is purely a wave. Easy. But then, as you see on the right, this completely radical new idea starts bubbling up. It suggested that this clean separation was totally wrong. Maybe matter could act like waves, and maybe light could act like particles. It was a direct challenge to the very foundations of physics.
This wild idea was officially put forward in 1924 by a physicist named Louis de Broglie. And here's the kicker. His hypothesis was purely theoretical. He just did the math and said, hey, what if everything, from electrons to, baseballs, has a wave-like nature? The problem was there was absolutely zero experimental proof. It was a brilliant idea on paper, just waiting for someone, somewhere, to prove it was actually real.
And this is where our main characters enter the story. We've got Clinton Davisson and Lester Germer working away at Bell Labs. And let's be clear, they had absolutely no intention of proving de Broglie's grand theory. Their mission was way more practical and, to be honest, kind of mundane.
Their goal was simple. They just wanted to study the surface of a piece of nickel. That's it. The plan was to shoot a beam of electrons at it and see how they bounced off. They fully expected the electrons to just scatter randomly, like throwing a handful of sand against a polished floor. It was a routine experiment, nothing more.
And then, the accident happened. A flask broke, air rushed into their vacuum chamber, and it basically rusted their nickel sample. So to clean it off, they did the logical thing. They baked it at a really high temperature. What they had no way of knowing was that this heating and cooling process completely changed their sample. It transformed the nickel from a bunch of tiny, random crystals into these large, perfectly ordered single crystals. They had, completely by accident, created the perfect target to see wave behavior.
So, they fix all the equipment, they put their clean nickel target back in, and they fire up the experiment again, totally unaware that the game had fundamentally changed. And what they saw next? Well, it made no sense at all.
Remember that random spray of electrons they were expecting? It was gone. Instead, they saw this, a clear, structured pattern. The electrons weren't just bouncing off randomly. They were coming off at very specific angles, creating these sharp peaks of intensity. Now, that is not how particles are supposed to behave. This looked exactly like a diffraction pattern, the kind of thing you see when waves interfere with each other. But they were firing particles. It was a complete mystery.
And in their 1927 paper, they basically came right out and said it. They noted that the pattern was consistent with diffraction. Even if they couldn't explain why it was happening, they knew they had stumbled onto something really, really strange.
So, the plot thickens. And the story's big climax, it doesn't even happen in their lab in New Jersey. It happens across the ocean at a scientific conference. In 1926, Davisson took a trip to Oxford, still carrying around this puzzling data, just hoping to find some answers.
And there, he got the shock of his life. Can you imagine? He's sitting in a lecture by the great physicist Max Born, and Born starts talking about de Broglie's radical wave particle idea. And as his key piece of evidence, Born presents Davisson's own strange results. It must have been this incredible aha moment. Davisson realized right then and there that his confusing, accidental experiment wasn't a failure. It was the missing proof for one of the most important new ideas in physics, a theory he didn't even know he was testing.
So, armed with this massive revelation, Davisson rushed back to the lab. Now, he and Germer knew exactly what they were looking for. The goal wasn't just to study nickel anymore. It was to systematically and very deliberately
prove that electrons act like waves.
So they refined the experiment. In their most famous test, they fired electrons with a very specific energy, 54 electron volts. That's just a way we measure energy for these tiny particles. And what did they find? A super sharp, intense peak of reflected electrons at a precise angle of 50 degrees. Now they had a hard number, a concrete result they could use to test de Broglie's theory directly.
And the results, they were a perfect match. Look at this. Using their experimental data, they calculated the electron's wavelength to be 0.165 nanometers. De Broglie's formula, which was pure theory, predicted it should be 0.167 nanometers. That agreement is absolutely stunning. That's not a coincidence. That is the smoking gun.
And just like that, their accidental discovery provided the first real, concrete, experimental evidence of wave-particle duality for matter. They proved that the stuff we think of as solid can, under the right conditions, behave just like a wave. It became a cornerstone of the new quantum mechanics.
The legacy of this happy accident is just immense. It didn't just confirm some wild theory, it helped build the very foundation of quantum mechanics. Davisson, rightly so, shared the Nobel Prize for this in 1937. And beyond all the theory, this discovery directly led to incredible technologies, like the electron microscope, which literally uses the wave nature of electrons to see things that are way too small for light to see.
And that brings us to a final thought to chew on. The Davisson-Germer experiment proved that on the smallest scales, reality is fundamentally fuzzy and, well, weird. It really forces us to ask, if the basic building blocks of everything, including us, can exist as both a point-like particle and a spread-out wave at the very same time, what does that really say about the solid, definite world we experience every single day? It's something to think about, isn't it?